TWR Garden. I'm here today to talk about making your website seem fast. Now, one of my favorite films is Top Gun, and in Top Gun, Maverick says, "I feel the need for speed." And I'm pretty impatient. I get really annoyed when everything's slow. So I like to make my applications feel fast. Today I'm going to dig into network layers, RFCs, and try to figure out what we can do to make things seem a little bit faster. So how do I know all this? Oh, I've been interested in making things fast in the world, but currently I work for a company called Fastly, where we make websites fast for people. So I've been digging into all of this stuff. So here's the big picture. You have your application at the top. We access it over a hypertext transfer protocol, HTTP, and then there's like a network thing at the bottom. I don't know about your application. You're the best person for that. So let's assume you've made your application as fast as it could possibly be. Or is there anything else we can do with HTTP and the network to make things faster? So what can we do with those two layers? Well, it's not really a network layer. There's lots of little layers underneath. But the main layer is the Transmission Control Protocol, Internet Protocol, which I'll generally call TCP/IP because it's shorter. And that runs over various other networks, things like a Wi-Fi, for example, or mobile data, or generically the internet, which has lots of other protocols, but we don't need to worry too much about them. The main thing about things like Wi-Fi and mobile is that there isn't much you can do to improve them apart from use the latest technologies that you can. So use wireless N or AC if at all possible, because there's less interference, because these things are over a shared resource. There's not a lot you can do about the internet things. So here is a web page on the internet. It is a Guardian page. It has a whole bunch of content, which is HTML, hypertext markup language, and there's one important image, and a whole bunch of other assets which you can't see. When your web browser tries to display this page, what it does is it connects with the Guardian servers. It says, I would like to request this page over HTTP. So there's an HTTP request, and the server thinks for a little while, and then responds with an HTTP response. So something like, "Hi, I'd like this page." Oh, okay, here you go. So I'm going to simplify for the next few slides, but it's basically all this. This is what a HTTP request looks like. It's an action, like I'd like to get this particular URL, and I'm this version of the protocol. And the host I would like to get to is the Guardian. And the response that comes back is kind of backwards, the reverse of the opposite of the request, which is the protocol, and then whether the response was okay or not. And then the various headers, things like the type of the content, so in this case it's HTML being sent back, the length of the content, in this case it's quite a big page, and then the actual content of the page. But more importantly, speed. What's fast? Light is pretty fast, right? In physics, the speed of light is represented by c. That's pretty fast. That's 300,000 kilometers per second. That's 1,000,000 times faster than the cruising speed from F-14A Tomcat, for example. And that's the maximum speed that light and information can travel. So when we think about things being fast, you'll think in seconds and milliseconds. And we are humans. Well, most of us are humans. And generally, you can trick your brain in interesting ways. So you have things like optical illusions, but you can also have temporal illusions. And with your brain, if two things happen within around 5 milliseconds, you can't tell that they were different. Your brain just assumes they were completely the same. You can generally tell if two things are around 20 milliseconds, if one thing happens 20 milliseconds after another thing. But then for some things, your brain is even more confused. If sound and audio in a film, if sound and video in a film is around 100 milliseconds off, your brain won't notice. It'll kind of fuse it all together and you won't notice. But more than about 100 milliseconds, your brain starts thinking something should have happened by now, or something's a little bit off. So more than that, you start waiting. I don't like waiting. So let's assume that our communication travels at the speed of light. It's not a bad assumption, because we generally go through glass fiber, and the speed of light through glass fiber is around 200,000 kilometers per second. That's good. So to send one bit of information from, say, a web browser in Heathrow to a web server in LA will take around, and back, will take around 90 milliseconds. So that's already quite bad, right? That's quite a lot of milliseconds. And that's just one bit of information. Doesn't sound very good. So TCP looks a little bit like this. This is how we set up a connection. So we're sending a few. First, we need to set up a connection, and then we can send the HTTP request. And it looks a bit like this. It's a hello, I would like to talk to you. You would like to talk to me? Yes, I would really like to talk to you. And then you can send the request. So when you see these arrows, you should worry, because the information has to fly across the Atlantic and back again, right? This is bad. Whenever you go from one side to the other, that's latency. Latency is bad. So just opening up TCP connections, like 70 milliseconds or so, that's before we even sent the data. So then your web browser sends the request, and then the server thinks for a little bit, and then sends it back. But it doesn't send it all back in one go. It sends a little bit back, and then goes, did you receive that okay? And you go, yes, I received that okay. It's like, okay, I'll send a little bit more back. Did you receive that? Receive that? Okay, yes, I did. And then it sends even more back and so on. This is because the internet blew up over congestion. And this is why we worry about congesting the path between two things. So we have slow start in TCP. And we use window scaling to scale the window. And this is all good and great for the internet, but it's bad for our latency, because it means that it's more round trips and things go slow. One good test, a good way to visualize what your web browser is doing is going to webpagetest.org, which is a good way to, because an HTML page has lots of different parts to it. For example, this Guardian web page has 149 different assets in it, which seems like a lot for a 600-word article. And it takes over 9 seconds to request all of these things. You can get little charts of how long it took. You can also do this in Chrome with developer tools, or in Firefox with web developer tools. You get much more information than I can present in a 20-minute talk. So for all of those little requests, it took a long time. And that's why it takes up to 9.2 seconds. The classic paper for web performance was written by Mike Belcher when he was at Google. And it's called More Bandwidth Doesn't Matter Much. So he basically looked at page load time, because people at Google care about page load time. And they looked at 2 different factors. So one was bandwidth, and the other was round trip time. So I guess you could pretend we call that latency for now. And the answer is, you can double your bandwidth, and your page load time doesn't go down by much. But if you decrease your round trip time, the latency, then your page load time also decreases by that factor. So when we think about ISPs, we should really care about latency. The bandwidth doesn't matter that much in comparison. The latency is much more important. So when was the last time you saw latency on ISP advert? Never, right? I don't care. I don't care about the web. Maybe I'll do something about that. Anyway, the big picture, the big equation we're going to try and minimize is this. If you have high latency and many big requests, then your website will be slow. So there's a couple of ways we can start attacking this. We can either have lower latency, or we can have smaller requests, or fewer requests, right? And that's what we're going to try and do. But maybe someone thought of this before. Maybe we should look at the specs. So HTTP was specified all the way back in 1996. A little minor update of HTTP 1.1, and then a little minor update later on in 1997. And then nothing happened. It was all a bit of PHP was kind of great, and we loved the web. And then we realized that everyone had kind of implemented it in slightly different ways. So in 2014, there was basically expanding upon, a slight cleaning up of HTTP 1.1. So it broke into lots of different RFCs, request for comments, kind of internet standards. And the one that's particularly interesting to me, I put in bold, is RFC 7234 on caching. It's like, that could be interesting. And more recently, there was HTTP2 specification this year. I'm not really going to talk about that. I'll mention it a little bit. So the main way you can make a website fast is to have fewer requests. So that's a relatively easy one. The Guardian page I showed had 48 images, 35 JavaScript files, and 2 CSS files. So they obviously spent some time having few CSS files, but not so much on the other ones. So you could combine JavaScript all into one file, for example, and that would be an easy way to go. You could also have all the images in one image, for example. That's called image spriting. So you have to do a bit more work when you're building your page, but there's lots of frameworks that can help you there. Another way to go is to use a TCP connection that's already open. Because opening up TCP connection involves round trips, and then you have the window scaling as you send more data around. So luckily, the great thing is that your web browser should already be doing this. So that's fine. Your web browser should already be doing this. There is one interesting way that you can get around this, is that web browsers, instead of sending one request and then waiting for a response, and then sending another request and waiting for a response, what you could do is send multiple requests all at the same time over the same connection. And HTTP, this is called HTTP pipelining. And so you should think that there will be less latency here. But unfortunately, while the spec says browsers may support this, none of them actually do. The main problem is that there were lots of buggy web servers which didn't understand this and broke things. So basically no clients do this. No. So sad. This is fixed in HTTP2. Anyway, and the great thing about window scaling is that people recognize there's a problem and that the internet is generally more capable than we used to think. So if you upgrade your operating system, so with Linux specifically 3.2 and above, then it scales Windows much faster. So that will also help with sending data back in as few packets as possible, so as few round trips as possible. One more way to go is if you send less data, then it will be faster. So many web pages are, shall we say, contain redundant things in them. So here are 3 random lines from this Guardian page. And there's so much redundancy over this. Like, why do you have to have all this verbose redundant information? If you can't find a way to remove this redundant information, the nice thing about it is that it also compresses really well. Ooh, compressing. We should do that. So the Guardian page is 380K or so. If you compress it using something like a zip, it'll get it all the way down to around 86K, which is good. So the way this works in HTTP is that the browser advertises as an extra header to the server saying, I can accept encodings, general compressions. I can accept these encodings. So I can understand gzip encodings. If you gzip your content and send back to me, I know what to do. And then the server goes, okay, here's some data, and by the way, I encoded it, compressed it in this way. And that's a very good way to save information. So in Apache, you'd use a mod-gzip, and Apache or various web frameworks have the same thing as well. But this means that you may now be sending back different information depending on the client. So it's probably best to be explicit about this and say, I may give slightly information based on this particular header that you sent me. So this is varying on information. So this will be interesting. This is very important for caches. So generally, you should be varying on accepting encoding at the very least, because you'll be sending back either compressed or uncompressed. And caches in the middle between the browser and you might get confused if you don't specify this, and it might send compressed content to browsers that don't support compressed content, and vice versa. So another way is to send not the whole object. So, for example, if you don't want all of the content, but only part of the content, only ask for part of the content. So if you send a range header with these bytes, this means I would like only the first 100 bytes of this particular image, or this particular content. So I've only ever seen this with with PDF viewers, for example. They fetch enough of the PDF to figure out the structure of the PDF. When the user scrolls down to a page, they only fetch the bytes for that particular, that they need to read for that particular page, because most people don't read the whole of the PDF. You also see this for video content as well. Most video has an index either at the beginning or the end, and with the index you can figure out which frames are at which timeline. So if you jump to 20 minutes into a video, it knows exactly which bytes to fetch. So that's a good way of not getting the whole information, because you don't want it all. And then we start worrying about not actually getting the data. What if we didn't have to ask the data? Maybe we already have a copy of it, and we want to know whether we can still use it. So this is not sending a response at all. So if you've already fetched a page, and if the browser already fetched a page, and then you go back to it again, maybe it hasn't changed. How do you know if it's changed or not? If it hasn't changed, you don't need to fetch it. So this is done in HTTP with the last modified header. So with a response, you can say this content was last modified at this particular date. And if you already have a copy of this and you want to check whether it's changed or not, you can send an if modified since, which says effectively, has this content changed since this time? And if it has changed, then the server sends back the whole content as if everything were normal, and if the header wasn't there. And if it hasn't changed, then it sends HTTP 304 not modified and no content. So you save on not sending the data back at all. There's one more thing. So similar to last modified is on time, and time may not be the best way to reference whether a bit of content has changed. And so we also have an E tag, which is an opaque tag. It's something like, you can tell the difference between different versions of your object with this tag. So something like a hash of the content or a version control identifier would do. So it has to uniquely identify a version of the content. So you've already fetched this content, and you've got a response from the E tag, and you cache it, and the browser caches it somewhere. And then you send if none match if you want to see it again. This means I would like to fetch this content as long as it's got a different E tag from the one I had previously. So if it has changed, then the content gets set back to normal. If it hasn't changed, you get 304 not modified as before. So I would probably use E tag rather than last modified because it's more specific. And then, instead of not sending a response, what if you didn't send the request at all? That would be a better way to save round trips. So this is all done by caching. Caching is a big subject, and the basic rule of caching is that you set a date in the future by which the content will have expired. So in this case, this is a response. The date is when the server generated this response, and expires is when the content expires. So you can tell there's 30 minutes between these two different dates. So that's the slightly older way of doing expires. The slightly more modern way is a cache control. So it's more explicit. It says in this number of seconds, the content should not be considered fresh anymore. So it's basically expired. So it's like that's also 30 seconds. That's also 30 minutes, but it's in seconds. One more way to do this is to have less latency. So you can't change the speed of light, but you can move servers around, right? So if all your users are in the UK, maybe LA wouldn't be such a great place for your servers. Maybe your servers should be in a data center in London City or something. Or in Docklands, so somewhere nearby. Because then it'll be quicker for all these requests to happen, and so the page load time will be less. Or, there's a problem with that, is that maybe your users aren't all in one place. Maybe your users are all worldwide. What would you do? Maybe you think that it would be great to have data centers that you like to, because maybe you think it's fun to run data centers, and you set up data centers all around the world, And you spend all your time negotiating with internet providers and figuring out routing problems and things like that. Or you could outsource all that to a company that does it. This is generally called a content distribution network. They're basically a cache for your content all the way around the world. So I work for Fastly, we're CDN, and these are all the nodes for where all the points of presence are, where all the cache nodes are. So your content will be cached at all the nodes, and so the round trips from users will be round trips to the closest POP, rather than back all the way to the original server. CDN spend quite a lot of time figuring out where the best place would be to have these interconnection points, and to have low latency for as many people as possible. The way a CDN works is kind of in between the user and the servers. So it goes, so it's, if something isn't cacheable or isn't cached yet, the client asks the CDN, here's a request. And the CDN goes, oh, I don't have this yet. Why don't I ask the server? And the server goes, oh yeah, I know about this, and gives it back to the CDN. And then the CDN caches it, and then hands it back to the user. So it might seem like an extra request, but the nice thing about this is that the CDN to server bit is generally optimized over the CDN's backhaul and optimized connections. So it's probably faster just having CDN and not doing any caching. It is faster having CDN and not doing caching than not having CDN at all. But the even better bit is that this is the good path. Is that your client asks the CDN, do you have this? And CDN goes, yes, of course, here it is. And the server doesn't do anything. The server's idle. So, so you can have less capacity at your server. And there's various things. The CDNs tend to do pay attention to cache control headers. And there are some other neat things you do. So one of the things you can do, in addition to max age, is things like stale while revalidate. If your content is just a little bit stale, and you're not using this, then the CDN will contact your server, cache it, and then send it back to the user. So the first user for a POP who asks for stale content gets an extra delay. So with stale while revalidate, the cache will serve stale content for a little bit, just while it revalidates, just while it fetches a new content with the POP, for a new copy, fresh content from the origin server. And also you can have stale if error, which if the server is serving errors, then serve old content rather than an error. So this is really useful. If you're the Guardian, say, and your servers die for a minute, rather than having a minute of errors, you serve a minute of old content. So old content might not be, stale content might not be a huge problem for the Guardian, for other websites it may be more important. If you'd like to have slightly different caching for the browser versus CDN, then you can also set S max age, so S is for the server. And so in this case, the browser would cache for 60 seconds, and the CDN would cache for 30 minutes. This might be useful if you have some sort of out-of-bounds way of invalidating your CDN cache. But my real rule is you should cache for things which aren't web pages. You should cache it for as long as possible. A year is very long in internet time, so a year is good enough. And if it changes, then it should have a different URL. This means that clients will notice straight away there's different content because it's got a different URL. So they'll fetch it as quickly as possible. So you use a hash of the contents for the URL or a version ID or something like that. In the future, lots of things will happen. I'm a bit slow. So TLS, everything's more secure these days, which is great. However, security comes with lots of round trips. Can you see that? So it's like, hello, I'd like connection. Oh, you'd like connection. Here's my certificate. Oh, let's pick these ciphers. Oh, you want these ciphers? Okay, now send the request. So the best thing to do with this is so you can optimize it a little bit, but the best thing to do is to have a CDN endpoint, just to CDN in the middle to just have latency. And I could talk about HTTP2 for an entire talk, but let's just say that the aim of HTTP2 is to have a reduced perception of latency. That's in the main synopsis of the talk, main synopsis of the RFC. And I haven't talked about it a great deal because it's not widely deployed yet, and we don't really understand how it's going to work, or how it works. There are some open questions as to whether it really needs to be that complicated, for example. But it's about reducing the perception of latency, which is that's the rest of my talk. So the thing you really have to remember is that only you can make the website fast. Thank you. I have a very brief amount of time for questions.
You commented that The Guardian had lots of bits of JavaScript, and websites like that. There might be one script to use on every page, and one bit on a couple, and one specific to this page. So I've got 3 of them on. I could combine them all into one object, but then of course if I serve that combined script to all pages on the site, some pages are getting more JavaScript than they need, which falls afoul of the content that you need. So I could then instead have a different combination script per page on the site, which each one is getting just one script with combined bits on. But that falls afoul of the caching, because when you visit the second page, you've got a different combination of scripts, and even though you've already got them locally, you haven't got them cached. So it seems that those 3 pieces of advice kind of contradict each other in the circle, which is the more important one to go for.
Yes. So the overall aim of this route is to minimize latency. And what you should do is you should measure the latency and make experiments and figure out what is better for you. So it turns out that The Guardian actually embeds a CSS inline into HTML pages, not because it should be better for them, but because it reduces latency. It means the CSS is already there at the browser and starts rendering quickly. So it actually makes things slower overall, but makes it seem faster. One more question?
How do you deal with user logins?
How do I deal with user logins? So there are some things which you cannot cache. And you have to bear that in mind, and ideally worry about it when you're designing your application rather than later in the stage. Anyway, I'll be here all day. Please come talk to me if you have any questions. Thank you.